to the exam review, one of the things that I am going to do, so some of these go together really nicely, and some of these I can do some broad strokes of. Some of these, though, are more difficult, but everything that's calling out for a particular um, properties of liquids, we can definitely do that. We can definitely talk some more about sigma and pi bonds. Intermolecular forces does frankly just take me a half an hour to 45 minutes to go through from beginning to end. So for intermolecular forces, I'm actually going to take a look at the questions my class asked me and see what I can do about that. So, but in general, there are four properties of liquids. Boiling point, surface tension, viscosity, and vapor pressure. And we're going to do vapor pressure last. And so we're going to focus on these first three because these first three actually all go together. Because the thing is that boiling point is trying to describe if I have a bunch of molecules and they have intermolecular forces between them, which they're molecules, they certainly do have that. This is water, this is hydrogen bonding and dipole-dipole interactions and London dispersion forces. This right now as it is, we're going to say that this is a liquid. And in order for it to become a gas, I have to basically have enough heat to break the intermolecular forces. So yes, suddenly these got bigger as well. But in order for this to boil, my water, my hydrogen bonding, my dipole-dipole interactions have to be disrupted. They have to break. They have to no longer be there. So here are my hydrogen bonding. So those are my hydrogen bonds in there. And now when I look on the right-hand side, there are no intermolecular forces, essentially. The molecules are now too far apart. But in order to do that, in order to pull that off, we had to add heat. So essentially, when we talk about boiling, we talk about adding heat so that the intermolecular forces are not strong enough to hold the molecules to the other molecules. And essentially what that means is that if I have stronger attractions as a liquid, stronger attractions are going to mean that I will need more heat to break apart. So there are a lot of different analogies that we can use for this. But I actually like the idea of things like magnets. So refrigerator magnets, these are usually thin or relatively small, like the ones that have advertisements on them. The one that are shaped like business cards. They're very, very thin. Um, and a small child can pull those off of a refrigerator without any problem. Because there is an attraction there, which is why the magnet stays in the first place, but it also comes off very, very easily. As compared to, we have things like strong earth magnets, which are also small, but they are mighty, and they can be very difficult to pull apart. Um, so that idea of stronger attractions, the stronger the magnet, the more energy, the more effort is required to break them apart. So that's what we're talking about when we talk about boiling point. This also means essentially that boiling point means that so that as intermolecular forces increase, we have a higher boiling point. The stronger the attractions, those are the intermolecular forces, the more energy is required to break them apart, which gives you a higher boiling point. We are going to say this same thing with surface tension. The higher the intermolecular forces, the higher the surface tension. That is because surface tension is also something that is better and stronger with better attractions. Viscosity, we're going to see the exact same thing. The higher the intermolecular forces, the higher the viscosity. The stronger the attractions in between the molecules, the less well the molecules actually flow against each other. So all three of those first things, the better the attractions are, the better that property does. So the stronger the attractions, the higher the boiling point. The stronger the attractions, the higher the surface tension. The stronger the attractions, the higher the viscosity. True for all of those. Vapor pressure is the opposite. Vapor pressure is going to be the higher the intermolecular forces, the lower the vapor pressure, because vapor pressure is not measuring, so vapor pressure is still affected by intermolecular forces, but vapor pressure is different because you're not measuring how well the liquid stays together, you're measuring how much of it goes into the gas phase. What I mean by that is, if I have a liquid hanging out, some of this will evaporate. So we will get some of that to evaporate. So this is caused by evaporation. And so once this, so we've got a lid on the box. So vapor pressure is basically measuring how much gas evaporates off. It is a little bit more complicated than that, because what we're really measuring is the pressure of that. So what I mean by that is, if I had something like a smaller box, I would probably have fewer particles, but I would still have the same vapor pressure because I would have a smaller area. So vapor pressure is measuring the pressure of the particles, which is something we'll get more into in chapter 11 when we talk about gases. The other part of this then, though, is if I had a totally different liquid, try to make the box look the same size, but it's a different liquid now. So some liquids just have more particles in the vapor phase. This is something you probably experienced in real life. So perfumes, colognes, if you pump gas at a gas station, all of those will give you a lot of gas particles off of the liquid. And so that's what we're measuring. We're measuring how much gas does the liquid give off. So in that case, essentially what we're talking about then is the higher the vapor pressure, would give you more gas particles. Well, in this case, the thing is that if you want more gas particles, if you're looking for a higher vapor pressure, you actually need lower attractions, because the real reason why you would get gas particles is because the attractions in between the molecules are weak. So essentially, again, thinking about the magnets, if you're trying to say, well, how many magnets can a little child who's not very strong pull off of the refrigerator, the weaker magnets are going to be what the small child can do. So so when you're looking for how can I get more magnets off of the refrigerator done by a small child who's very weak, the weaker the magnets, the more they can pull off. So hopefully that helps with vapor pressure and boiling point and intermolecular forces. So in the original review, I had gone ahead and demonstrated the fact that in our e-learning page, there are videos that I made of in the 701 section for intermolecular forces. So for those of you that really wanted to hear intermolecular forces from the beginning, you have that opportunity, but they're hanging out in the 701 section in pre-recorded lecture videos 2020, chapter 7 materials, and there is one on intermolecular forces. And I made this one, this is me. So this is all trying to talk about the different intermolecular forces. There's also one in there on properties. Actually, there might not be one on properties of liquids in there. It's probably in chapter 12. But regardless, polarity of molecules, electron domains, all that stuff is in here if you just wanted to hear everything from the beginning. So what I am going to do is I'm going to take some time to basically look at some more of these questions, which I know might be too small for y'all to see. So I will be reading them out loud as we go along. How are dipole-dipole interactions different from polar-polar bonds? They're, so it depends on how we're talking about this. So in general, if I have something like something that just has dipole-dipole interactions. So here's carbon with one chlorine and a whole bunch of hydrogens. This chlorine is more electronegative. My carbons and hydrogens are all nonpolar. So this chlorine having more electron density towards it is going to make my molecule overall polar. So in this case, because we have a polar bond, um, and there's only one of them, this is also a polar molecule. That polar bond and the polar molecule gives me a dipole interaction. And then it's the fact that when I'm talking about the intermolecular force, then I'm talking about the fact that I have multiple of these molecules, and multiple of these molecules will essentially line up where I have a partial negative where the chlorine is, partial positives where the hydrogens are. Negatives for the chlorine, positives for the hydrogen. Negatives for the chlorine, positives for the hydrogen. And those positive and negative are attracted to each other. And this is also, you could also look at this with a dipole moment. So you could also look at it as the positive and negative portions, because essentially the molecules are lining up with their dipoles. The molecules are lining up because they have positive and negatives attracted to each other. So they are lining up like little magnets. So the idea of polar molecules and dipole-dipole interactions naturally go hand in hand together. So the question is, what's the difference between them? It really depends on the exact wording, because we could ask about polar bonds, we could ask about a polar molecule, we could ask about dipole-dipole interactions, and we could also ask how all of those things go together. So a lot of that's going to be reading the question carefully or reading a statement carefully to make sure that you know if we're trying to ask you about something that's inside of the molecule, like a polar bond, something that is about the molecule itself, is the whole molecule polar or nonpolar, or are we trying to ask you about the interactions in between the molecules, in which case that's the intermolecular force. But all of those things build up, right? All of those things build up together. So this is similar to how, like, as human beings, you can have something that is happening inside of you. So let's say something like a virus, where you don't feel so good. And so you can talk about the virus inside of you and how your immune system is working on attacking the virus, and all of those things are happening inside of you. But you can also talk about outside of you, how you as a person then are coping with the various symptoms that you have because there's a virus inside of you and your body is attacking the virus. So you could talk about that on a molecular level inside your body. You could also talk about the fact then that you might have a fever, or you might have a cough, or you might have different symptoms that go along with that. And then you might also talk about the fact that because you have those symptoms, maybe you are going to like stay home more than you normally would, or maybe you're going to tell your friends, hey, I know we were going to get lunch today, but I don't feel good, so I'm not actually going out. So you could talk about the virus inside of your body, you could talk about your own symptoms as a human being, or you could talk about how you interact with the world around you. But they all have to do from a similar standpoint. So I definitely understand the question about like, how do these things all go together? Because they do, but also we could talk about them on different levels as well. How do we find the number of sigma and pi bonds in a structure? What exactly do we look for? I didn't address sigma and pi, even though that one got asked about. So if the goal is just to count sigma and pi, then counting sigma and pi, one of the main things to be aware of, do this guy. So if we're just trying to count sigma and pi, and it's in a structure that looks something like this, and that's not supposed to have, anyway, that's just supposed to be a hexagon. So those are not supposed to look like that. Well, hold on. Yes, you do get, so that's just whatever. That's, oops, that's going to be a carbon too. So one of the things with sigma and pi bonds you do want to keep in mind is how many bonds are there really? So this is where for your line skeletal diagrams, keeping in mind what's really going on in there is really useful. So as we go around, we're going to start at the top. carbon has two single bonds, it needs two more. This one's got two single bonds, it needs two more. You're gonna have that happen all the way around here, essentially, except when we get to this carbon, which already has a double bond and a single bond, so it just needs one more, and that one also just needs one more. So for pi bonds, we just need to count the fact I have this lovely one double bond here. So there's only one pi bond. For sigma, on the other hand, I got to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Gosh, I hope that's correct. So double bonds have one sigma and one pi. Single bonds only have a sigma bond. When we talk about sigma bonds and pi bonds in general, one of the things to keep in mind with sigma bonds is that sigma bonds are, where are the pictures that I like? So sigma bonds are always about head-on overlap. There's different ways to phrase that. So head-on overlap, end-to-end overlap, single lobe overlap. But sigma bonds are all about the fact that you have two nuclei. So those little dots in the middle are supposed to be the nuclei of the atoms. And as the electron clouds overlap, you have a bond. So these are two S's, and when they overlap, you have a sigma bond. Two p orbitals can overlap, and you still have a sigma bond. Hybrid orbitals can overlap, you still have a sigma bond, and etc. and on and on. When you have a pi bond, however, those are p orbitals. So they're typically referred to as unhybridized p orbitals, but they're just atomic p orbitals, and they're also overlapping. The thing is, though, is that because we already had those lovely sigma bonds, those sigma bonds are already taking up the space in between the two nuclei. So those dots I have are the nuclei of the atoms. And my sigma bond is already taking up all of the space right in between them. So a pi bond has to have a new space. And that's where my pi bond basically goes above and below. As you might imagine in 3 dimensions, you can also do this in front and back. So that's a little bit difficult to show. Your textbook does, though, take a swing at it, and that looks like this, where it's doing one pi bond above and below, and a second pi bond in front and behind. That's what's actually happening there in that setup. But that's how we actually get this particular set of which bonds are which as we go along. So hopefully that helps with sigma and pi bonds. This is always my struggle when I'm doing the exam review, is we could talk about so many things, but hopefully that's enough to get you guys started on there. A review on geometries and their relation to polarity of molecules. I think I already did this in the original exam review, so I'm going to keep going. What are some ways to remember and know electrons are distributed in hybridization? Like which ones are in hybrid orbitals and which ones are not? So in general, for knowing when something is in a hybrid orbital, let's come over here and look at something like ammonia. So first of all, if it counts for electron domains, it is in a hybrid orbital. And what I mean by that is I've got the nitrogen has a lone pair, and then I've got these lovely bonds right here. So my nitrogen has to be sp3 hybridized. So the nitrogen is going to have a lone pair in hybrid orbitals, and then it's got to have electrons ready for bonding. That being said, you just assume that hydrogen is not, I assume hydrogen is not hybrid. Hydrogen only has one electron to give. So that lovely little like 1s electron from hydrogen, there's no reason to hybridize that orbital. It's just going to hang out in a sphere. And that's it. So there's that. Then the other piece of this is pi bonds, which I don't know, I need a different molecule for this. Pi bonds are not hybrid orbitals. Let me show you what I mean by that. So we were just looking at pi bonds and the fact that you needed two overlapping p orbitals. So if I'm trying to describe the we'll just do all hydrogens to make my life a little easier. So for valence electrons, so let's think about this for valence electrons now. Um, so valence electrons, this has 2 carbons. So this is 2 times 4, plus there's 4 hydrogens. So 8 plus 4 is 12. So I should be able to take this molecule and describe where all 12 electrons are, because there should be 12 electrons hanging out in, did I do that right? 2 carbons, 4 hydrogens, 2, 4, 6, 8, 10, 12. Yes. Sorry, before I go too much further, wanted to double check and double count. Um, so there should be 12 electrons in here in the valence, which means I should be able to tell you how many of those 12 electrons are in hybrid orbitals and how many are not. So first of all, we have 2 central atoms. They are the same, but there's still 2 of them. And when I look at my central atoms, I've got 1, 2, 3 electron domains for one of them, 1, 2, 3 electron domains for the other. So each carbon, these are both sp2 hybridized. So as far as each of my carbons are concerned, it's got sp2, and of the 4 electrons that each carbon brings, because the 2 carbons are the same, 3 of those electrons from each carbon are in sp2 hybrid orbitals, and one of them is in an unhybridized p orbital. So each carbon has the same setup. So the carbon on the left looks like this, and we'll go ahead and make the carbon on the right and draw the diagram for the carbon on the right. It's the same, it's the exact same, but that way if we're trying to count individual electrons, you can count all of them. So I've got all of my, so this is what my 2 carbons should look like. They're sp2 hybridized, but each carbon brought 4 electrons. Now, what's happening here is because these are all forming bonds, every hydrogen is bringing that 1s. So hydrogen is bringing 1 electron and 1s every single time. So for all of these interactions, so essentially I have 4 of these for each hydrogen. So, and that actually yeah, and that actually gets me all of my electrons. So I have 1, 2, 3, 4, 5, 6 in hybrid orbitals. And then I have 1, 2, 3, 4, 5, 6 in unhybridized orbitals, because I've got these guys. So that's one way to do this. The other way to think through this, so for those of you that are like, I don't know that I liked that, here's the other way to think through this. So we're still going to go with the every hydrogen only has the 1, but we could also draw this out in a different way. So I'm still looking at a carbon, and then I'm going to have a sigma bond, right, to my other carbon. So those are hybrid orbitals. So here are all of my sigma bonds. Because as I look in here, I should have 1, 2, 3, 4, 5 sigma bonds. So from my sigma bonds are being formed from, these are my hydrogens. So my sigma bonds are being formed from 1, 2, so these 3 black ones on this carbon and these 3 blue ones on the right-hand carbon. Those are my hybrid orbitals. And this gets me, so right here, right now, currently have 6 electrons in hybrid orbitals from the sigma, from looking at my sigma and pi bonding. And then I have right now shown 4 electrons in atomic orbitals. unhybridized orbitals from all the hydrogens. But if you'll notice, that's only 6 and 4. That's only 10. I only am showing off my sigma bonds right now. The thing I'm not showing is the pi bond. So if I'm going to show off my pi bond, I need to show what's happening. So my pi bond is that above and below thing, where basically I have overlap from a p orbital on each carbon. So I have one electron essentially from each p orbital. And so then I have 2 electrons in the pi bond, which is also, since it's just coming from 2 p orbitals, those are also unhybridized. So you can look at what electrons are in hybridized and unhybridized orbitals, either from a standpoint of hybridization, or you could also think about it in terms of sigma and pi bonding. You do still need hybridization for that because you need to look at like the central atoms, but it is definitely doable. It's definitely doable. What are some questions that could be asked about hybridization? How do you apply the concept? I'm hoping that the example I just did can go over that, because essentially for the drawing that we just did, for either ammonia, for either the ammonia molecule or for the more complicated one with carbon and the double bond and the 4 hydrogens, we could make a list of true and untrue statements, either about how the sigma and pi bonding works, how the hybrid orbitals work. So there's a lot of different words that could go along with all of that. In addition to counting, right? There could also be statements about there are 12 electrons all in hybrid orbitals. Would be incorrect because some of those hydrogens should be unhybridized. Could you explain the concepts behind when the bonds are polar but the molecule isn't? This is one I think I did in the exam review, but I'll go ahead and give an example again. So when the bonds are polar but the molecule isn't. So we actually using something that is relatively fast to draw, I hope. So here's carbon with all chlorines. Carbon with nothing but chlorines, all the chlorines. So even though I have all chlorines, and yes, this definitely has polar bonds, so there's a little dipole moment going out to each of the 4 chlorines. Every single chlorine is essentially pulling the same amount, is trying to get that electron density towards itself, and they're all doing this equally. So all of your chlorines are trying to get the electron density towards themselves, but because they're all doing it exactly the same, nothing actually happens as far as polarity is concerned. So there is more electron density on the outside of this than there is on the inside of the molecule, but it's all evenly distributed. So this is still evenly distributed electron density. And that means that this is a non-polar molecule. So all of that electron density is evenly distributed. That means this is a non-polar molecule. Hopefully that's helping. I'm still struggling with limiting reactant and excess reactant problems. So those we did for the original exam review. I'm going to leave those behind for now. The one thing I will remind you is that there's 3 ways to do that. 3 ways to calculate. And because there's 3 ways to calculate that, do make sure as you're learning limiting reactant and as you're practicing limiting reactant that you just pick one. Pick one way. It's really tempting to be like, well, which one's the best and which one's the fastest? And the best way is the way that you understand, and don't change it. A trick to remember Vesper theory and dipole explanation. Honestly, I don't know any tricks. So I definitely respect the like, is there a faster way to do molecular geometry? I've never known it, which is part of the reason why in class I went ahead and took time left a lot of space for dealing with the fact that these are three-dimensional structures. So if there's a trick for Vesper theory, I honestly have never learned it. There probably is, there always is. The internet is full of ways to memorize things, but Vesper I really don't know a trick for. How can I compare or determine if there's hydrogen bonding when the molecule is surrounded by other molecules of itself versus surrounded by water molecules? Alex asked. I would actually tell you not to worry about this. We are going to do intermolecular forces with just the compound itself. So if you are curious about that particular Alex topic, where it was asking about the water, come talk to me in office hours because I think it is interesting, but it's a little bit more than what we need right now. We're just going to do intermolecular forces with the compound by itself. So if that part made sense, you are good to go. Will electronegativity for elements be given on the periodic table? No. So the way we expect you guys to know if something is polar or nonpolar is essentially it's nonpolar if it's the same element or if it's carbon and hydrogen. And basically, we just assume that everything else is a little polar. Is at least a little polar. It is a big assumption, I'm not going to lie. So basically, we have a definition for nonpolar where nonpolar is either the same element or it's a carbon bonded to a hydrogen, and everything else is at least a little polar because no, we're not going to give you the electronegativity values. That's how you can handle that. What's the difficulty of this exam compared to other exams? I'll be honest, I don't know. Part of the reason I don't know is because some people are still not happy about dealing with Lewis structures, and you still need Lewis structures. Other people are fine with Lewis structures, and maybe they even remember some of the molecular geometries from high school. And so this exam is really difficult to judge because in general, it's very cumulative, which should make it more difficult. Because in general, the more you're having to rely on information that we've already done before, it's usually more challenging. So we have very little in this exam that is brand new. And that does not rely on skills from exam two. Almost everything that we're doing relies on exam two in some way, shape, or form, which does make it more challenging. Some folks, though, are still relying on memory from high school, so some folks will not agree with me on that one. How are pi bonds planar? And since they're planar, how can they have above, below, front, and back? Yes. So I like drawing things, even though I'm not that good at it. So here's the deal. So this especially comes up when we think about things like this shape. We could also do it in the other shape that I drew, because this is planar as well. So first of all, planar is relative. The idea is that these carbons here have a double bond, two single bonds. So both of these carbons are sp2 hybridized. These carbons, you would find the same thing, essentially. 1, 2, 1, 2, and there's a hydrogen here. There's hydrogens basically on each one of these carbons. Each carbon in the hexagon is sp2 hybridized, all of them. The thing is then, if I could take this hexagon and I could put it where we're looking at it on edge, my pi bond or my hexagon then is above the hexagon and below the hexagon. So the hexagon itself is flat. So when we say this thing is planar, we mean that the hexagon, the atoms, are all in the same plane. The carbons are all in the same plane. The hydrogens are all in the same plane. That's what we mean when we say flat. The pi bond does then make it like a sandwich where you have above and below. So once we hit sandwich, you could definitely make the argument that this is no longer a plane because a sandwich is more of a three-dimensional object and it's not really all flat. But you could hopefully, when you think about this as like a hamburger or a sandwich, you can still kind of get the idea that now we have layers, right? They're a bunch of flat things that all go together. That's what's happening with your pi bond. Same thing in my carbons and hydrogens over here on the right. I'll try to draw these like it's on edge. Oh no, I can't really do it. Um, this is not, this is just smaller. This isn't better. It's just smaller. Anyway, my hydrogens are going off like this. My hydrogens are coming out like this, going out like this, coming at you like this. I'm actually going to erase the thing I drew in the middle because I'm going to try to go ahead and draw that as a sigma bond. Great. And then again, I should have a pi bond, but my pi bond should be above and below. Um, so the idea of things being planar or flat, we have an emphasis on the atoms themselves, and then the pi bond is going to add another dimension, essentially. But no, so good point that when we do talk about planar molecules, with the emphasis is on where the atoms are. Those pi bonds, because they're above and below, they won't be in the same plane. How much do sigma bonds overlap? What determines how much overlap? How much do sigma bonds overlap? This depends on a few things, including what we're talking about when we say how much of it is overlapping. So what I mean by that is if you look at the P to P versus the hybrid bonding, you can kind of see that the hybrid to hybrid orbital actually has more space in the middle for that bond than the two p orbitals overlapping. So you could make an argument that hybrid orbitals do actually have better overlap because of that. There are different things in sigma bonding where you do have differences. That's kind of hard to describe if you look at the two s orbitals, just because the s orbitals themselves are a bit smaller in general in this particular diagram. So trying to talk about like what percent of all the electron density is overlapping, it's an interesting question for visualization, but it's more something that's just interesting to consider. It's not something we would test on, aside from maybe the hybrid orbital is better, because part of the advantage of hybrid orbitals is the fact that you have more electron density in between the two nuclei. So I can see an argument for having an exam question about hybrid orbitals being better at bonding because of their shape and because they get better overlap. That I could see. The rest of it, though, not so much, aside from just comparing hybrid orbitals to atomic orbitals. Will different limiting reactant finding methods work better on different types of questions? Technically, yes, but honestly, I still think for limiting reactant, I think the way that works best is the way that comes to your mind first. And I think you're better off just knowing how to do limiting reactant one way really well than having an arsenal of different types. Valence bond theory. Valence bond theory really is just, so valence bond theory is really just the fact that you need single electrons in orbitals to overlap. So valence bond theory is the reason why when we were counting electrons over here, these all just have one electron in the orbital. Because valence bond theory basically says, hey, those valence electrons all need to be in an orbital available for bonding. So part of this drawing that we have is actually because of valence bond theory. We're trying to make the argument that I have electrons ready to go in an orbital by themselves, ready to overlap. That's valence bond theory. And that's part of why valence bond theory always seems like we never do it, because it takes about 2 minutes. We have to recognize hybrid orbital diagrams on the exam. I can't answer that. Valid question, but I don't really know the best answer to that one. Because there's enough about the concepts about hybridization that some of you would potentially find that helpful. So I don't know how to answer that question in a way that's good. Will we have to guess products from reactants or vice versa when trying to balance an equation, or will the molecules be given to us? We give you the equations. So we give you reactions. Now, keep in mind that while we will give you the reactions, we could do that all in words. Question mark. So you do not have to predict any products for exam 3. Predicting products is something you will do on exam 4. So that is coming up this semester, but that is coming up in exam 4. How does resonance fit with Vesper theory, and how likely are we to see it on the test? Um, as far as resonance goes, so basically, and this was in Alex. What is a molecule that Alex did? Let's do phosphate. I don't even know. I don't remember which molecules Alex did and which ones they didn't do. But Alex basically did something like this. Um, so here is phosphate. Kind of wish I grabbed something from the last exam. Anyway, doesn't matter. Here's phosphate. We'll go ahead and stick the charge on the outside too. Here's phosphate. If I was asking for deviations, at a first glance, this looks like this has deviations because of the double bond, but this has resonance, which means that this is really all equivalent bonds. So this is the truth. So this means all bonds are equal and that there are no deviations. So even if I wanted to tell you the actual bond angles, this is tetrahedral. So this has 109.5 degrees as its actual bond angle because it has resonance. So even though when you draw the Lewis structure, it looks like there should be deviations because it has a double bond and 3 single bonds, that Lewis structure is lying to you. That Lewis structure is an oversimplification. Phosphate has resonance, which means that that double bond is really spread out evenly across all 4 bonds. Since it's spread out evenly across all 4 bonds, there is no deviation, and the bond angle should be 109.5 since this is a tetrahedral molecule. So that's how resonance would apply. Is resonance would apply the same way that Alex actually tested you on it, or Alex challenged you on it, was to look at, does the molecule have variations on bond angles due to its bonding, and you have to keep resonance in mind when you look for that. So that's the way I think that would come up. Because otherwise, most other things for resonance, it wouldn't matter. But deviations is where it would matter. Oh, okay. How likely are we to see it? Don't know. No more than once. Is there any easy way to remember how to draw certain Lewis structures, their geometry, and electron domains? I completely understand wanting to know, is there a faster way to do this? I don't know. Valid question. I don't have a fast answer for this. Since we now know Vesper, how do we draw Lewis structures? So Lewis structures are still Lewis structures. What I mean by that is, even though I know I drew this carbon with the chlorine and the 3 hydrogens to try to give you an idea of shape, a Lewis structure still has just everything connected. So Lewis structures don't have shape, gives no shape information. So it's a good thing to remember that Lewis structures don't give you any shape information. And honestly, if we ask you about shape for a short answer, we're just going to ask you to name the shape, because drawing these shapes is something that is challenging even for me. By now, y'all have seen me kind of struggle to do a good 3D representation, especially quickly. So honestly, we don't ask y'all to draw the Vesper shapes on your own for the exam because it's very difficult to honor what you know about shape by a drawing when you've had about 2 weeks to practice. Um, so that is something that they will do in organic chemistry. So don't worry, that skill will be tested. That skill will be tested in about a year for those of you that have organic chemistry in your degree plan. So don't worry, We'll get there, but somebody else. If it's asked in a multiple choice or free response, what's the angle between two atoms? Is trigonal planar with a double bond? Um, so the question is kind of about ideal and actual. So just keep in mind to read the question, because we can ask you for an ideal angle, in which case we just want that. So this was about trigonal planar specifically. Um, the ideal angle is always 120 no matter what's going on. If you do have something where you have deviations, um, then the ideal angle is still 120 degrees. Um, so the ideal angle is still 120 degrees. The actual angle is what changes. So that's where then this one for A would be less than 120 degrees, and B over here would be greater than 120 degrees. But the ideal angle is still 120. So that's part of using that language, is actual or deviations mean changes. Ideal means just tell me, hey, you have 3 electron domains, that's 120 degrees. How close do atoms need to be on a periodic table for them not to have a significant polarity difference? I've already answered that question. We're just going to go with the same element or carbon and hydrogen to be nonpolar. This question asks, let me draw this out. So this question basically, and it's a valid question, it basically says, hey, if I have something where I have nitrogen and fluorines, I know because of the lone pair on nitrogen that this is trigonal pyramid. So I know that this is polar. But the question is, which side is more negative? And I'm going to tell you, I don't know without looking it up. Because you've got fluorines that are really electronegative, and you have 3 of them. And so so basically what we would expect you to know about this is we would definitely expect you to know that this is polar. That you can definitely know. So you could still do intermolecular forces off of this thing. You could still tell me lots of things about this. But basically we would not ask you which side is more negative. We would not ask you to draw a dipole moment on this thing, because I'm looking at it and I'm like, do 3 fluorines are 3 fluorines more negative, have more electron density than 1 lone pair on a nitrogen? Fabulous question. I would have to look that up. So if I have to look it up, it's not an exam question, because I do not know. So there's another point about the Alex and the water molecules. I'm gonna just do that one in office hours because I think that'll make more sense in a one-on-one setting to deal with Alex and water molecules. When a double bond is present in a trigonal planar shape, a triple bond or a lone pair takes up more space than double bond. Do we still just say it's 100? Yes. So basically the question is if I have 3 different things. Let's not do carbon. So the question is if I have this versus a triple bond versus a lone pair. In general, if these were actually the same, which this is not, these are not real molecules. In general, the double bond is going to have the least deviation, and the lone pair will have the greatest deviation. So basically, you would expect this to be in here to be less than 120 degrees, this to be smaller than 100, smaller than the other one, and this one to be the smallest. The hard thing is that you'd have to have this set up perfectly in order to do that. Because if the hydrogens change to other atoms, that could change. The fact that I'm not sure what setup we would actually have, where you could just swap out a double bond for a triple bond for a lone pair on the same atom. So in a perfect world, we could definitely say you would expect a greater deviation from a lone pair and then a triple bond and then a double bond. But actually having things where you could directly compare without any other confounding factors is impossible. Um, so if you, all other things being equal, this works fine. Because we have a tendency to do real molecules, this is difficult to actually find good examples of in real molecules, which is why we wind up showing y'all like a double bond versus a lone pair, because those we can sometimes find decent examples of, but it's difficult to find all three of these without other factors also happening, because size of atoms start to play a role, things like that. Well, we have to memorize the Pauling scale. No, do not memorize the electronegativity scale. We've done that one. Do we have to consider molecular geometry when determining intermolecular forces? Yes, you do need molecular geometry when determining intermolecular forces. Um, and it gives a particular example, and it's a really good example of why the answer is yes. Good call. So this goes back to Lewis structures not giving you shape. So I'm going to go ahead and draw the molecule that was in the question. So here is the molecule. This thing has 4 electron domains. It's bent. It's polar. It has a dipole moment. So when we look at intermolecular forces, this has dipole-dipole interactions, and this has dispersion forces. Dispersion forces. Now, I've already mentioned, but this is a really good example of it, that Lewis structures can lie. If this is a Lewis structure, this is a Lewis structure of that same molecule. There is no shape information here. But it looks like there is, but there isn't. So the thing is that if all you had to do is go off of a Lewis structure, what we do is we'd still go ahead and say, well, this has 1, 2, 3, 4 electron domains. So since it has 4 electron domains and 2 lone pairs, this is actually bent. Therefore, it's polar. I know it doesn't look like it's polar. That's because I drew it like a Lewis structure, and the Lewis structure does not give shape information. So this is perhaps also where the questions that I've been seeing that are asking, do we have to draw shape? This is the best example of why, yes, you should practice drawing the shapes is a better answer. So when people are asking me, do I have to draw the shapes? And I'm like, no, you don't have to draw the shapes. But here is the place where if you don't draw the shape, it might get you the wrong answer. Now notice, as long as you acknowledge that what you drew is a Lewis structure and that Lewis structure does not tell you shape information, you could still go ahead and say, well, that means I'm going to rely on counting electron domains. Because in a Lewis structure, you can still count electron domains just fine. So that would be my personal strategy at this point, is to just draw the Lewis structure, but tell myself that the Lewis structure doesn't give me any information about shape. So I'm going to draw the Lewis structure, count the electron domains, and rely on my knowledge of electron domain geometry and molecular geometry just based on how many lone pairs are on the central atom and how many electron domains I have. Because you can still get that same information. But what it looks like to the human eye can play a role. So keep in mind that the picture on the left is the shape picture. The picture on the right, there's no shape information to give. So this is a good example of why practicing drawing the shapes is helpful to understanding the other components. Will there be a holistic review this week to review everything needed for this exam? No. I appreciate the fact that that would be helpful. I've been in a couple of meetings where that's been recommended. And then that might turn into a summer project, but a summer project is what that is. What's the order for finding bond strength, dipole, London dispersion, hydrogen? So yeah, so just ranking intermolecular forces. Um, so for just ranking intermolecular forces, we rank hydrogen bonding. We're going to talk about, so I'm going to rank ion-ion first. We'll come back to this. Then hydrogen bonding, then dipole-dipole, and last London dispersion. Now, here's the deal. I know ion-ion forces, you can make the argument that an ion-ion interaction is an intramolecular force as opposed to an intermolecular force. The reason why I went ahead and labeled and went ahead and put ion-ion on the list is because if I ask you which has the higher boiling point, which has higher boiling point, and I give you sodium chloride versus water, you need to tell me that sodium chloride has the higher boiling point, because it has whole charges, right? This is sodium chloride. I'm not going to grab the periodic table, but that is a positive ion and a negative ion that are attracted to each other. That has a really high boiling point. Water has partial charges. That's the reason why every time that we draw water, we draw that little weird symbol to go with it. I know there are these lovely hydrogen bonds in between the water molecules, but when we talk about it, that little figure eight thing is to try to demonstrate the fact that it's not a whole charge. The other way to think about this for boiling point, y'all, you can boil water on the stove, right? Like there are appliances in the kitchen that will let you boil water. Do not try to boil salt, table salt on the stove. You will just destroy your pan, or destroy the pot that you have that in. You will possibly get harmful chemicals into the air because you'll have a pot with nothing except sodium chloride in it, and the sodium chloride will not melt with what your stove can do. It will not. Um, so yeah. So sodium chloride has a higher boiling point, which is why I put ion-ion on here, because whole charges are stronger attractions than partial charges. But that's the order of the strength. Will we be going over molecular geometries again? Nope. Come to office hours. What topics are going to be most tested? You'll find a little more on chapter 7 than on chapter 8, much like we spent more class time on chapter 7 than chapter 8. But other than that, I don't have a great answer for that. These are starting to repeat, which is understandable. So basically, I asked my class on Monday for questions. But I think at this point, I've answered most of these. So in general, if there is something that you wanted me to talk about that I did not get to, that is because I've done my best, but because I didn't do a great job of filtering these, which is my fault, I'm having problems finding the unique questions in the time that I've allotted myself. One thing that I do see in here that I can't answer is diatomic. What does diatomic mean? This one I can answer quickly. Can't spell diatomic. So di means two, and this is the word atom. So diatomic is what we mean when we have things like oxygen or hydrogen, and we have a set of elements that naturally form diatomic molecules. So we called those the homonuclear for same nucleus. So being the same element, same nucleus. So same nucleus, so two atoms. And that was either Brinkelhoff for bromine, iodine, nitrogen, chlorine, Brinkelhoff, hydrogen, oxygen, fluorine, or with a periodic table. Pardon me while I scroll desperately. Where was that thing? Oh, there's one. Or the other way to remember the homonuclear diatomics is with that like Magnificent Seven thing, where you basically draw the number seven or shade the number seven on the periodic table. But then you got to have something to cut to hydrogen. So I've seen it as like star seven um, in order to remember all the homonuclear diatomics. Um, I've also heard Magnificent Seven because there's seven of them. Um, Magnificent Seven was a movie, by the way, for those of you that don't know that, that's okay, by the way. You don't need to know that Magnificent Seven was a movie. Um, but that's why they call it that, is because the Magnificent Seven was a movie. So for some people, it's easier to remember. I've never seen it, so I have no idea. Okay, this is now about an hour long. So what I was saying is, if there's specific questions you still have that I did not get to, basically just ask me again. I'm doing my best at this point to try to keep up with email, which I'm failing at. Um, but I'm going to do my best to get caught up on some of these things today. So also why this video is later than it usually is. Good luck on the exam. You can do this. Bye.